one. Searching for an item by value, so you want to find a particular value in the array, is still ON, order N, because it does depend on the number of elements, because if you have more elements, you have to search more on average to find the right value. You're not using the index. There's a huge convenience, though, in being able to store heterogeneous types, including other collections in one array. So you can literally have an array list or it contains array lists in Java, or a Python list of lists. And this enables you to build some really sophisticated data structures. Insertions and deletions are still kind of a lot of trouble, though, worst case, since they may involve moving a lot of data around in memory to make room. Imagine you want to insert something at the beginning of the list. That means all of the indices, all of the values of the indexes need to move down one. Now, you don't necessarily need to copy all the data that's pointed to, but you need to adjust the indexes. And that may mean a fair amount of copying in the array, and it's probably very dependent on the number of elements in the array. The worst case, of course, is inserting something at the beginning, and the easiest case is appending something at the end. Now, there are other data structures that work around these limitations, and we'll talk about them in this class. If you're willing to give up the constraint of contiguous index storage, okay, no, there's no longer the index values are no longer side by side, so you can't use address calculation. You can use some other data structures that are better suited, for instance, for insertion, deletion, and sorting and searching. There's a family of linked structures. You might have hit on these in your C programming class if you programmed a singly linked list. Remember, you had a number of nodes that were linked together with pointers. Those are the simplest kind of list structure. And you can have doubly linked lists, circular lists. They use, rather than indexes, they use pointers to tie together the elements, so you can chain from element to element to add, delete, or find the elements as you want. Tree structures, they're kind of like lists. These use pointers, just like lists do, to link the elements, but they're organized so that searching efficiency is improved. So they're pretty much already stored in sort order in many cases, making it possible to use very simple binary search variant of the binary search algorithm, which makes it much quicker to find the value, a node by value, than it is if you had to search the whole array in a linear fashion. And finally, there's hashing. Hashing is a term for a fancy form of address calculation. It's a generalization of the address calculation we do in arrays that enables you to go more or less directly from a key to the value that you want. Of course, the beauty of hashes is the keys don't have to be integral types anymore. They can be strings, and they can be object valued. That opens up a lot of possibilities. They use a combination of sophisticated address calculation and they use lists as well to handle what happens when several keys hash to the same value. So they're kind of combination structures. Python uses them extensively in their dictionaries in Python. Very, very handy. A lot of Python stuff is built internally on using these hash structures. So in summary, arrays they're probably the first, and they might be the only data structures you've used in coding so far. They're simple, fast, easily understood, and they form the basis, a good basis, for learning about other more sophisticated data structures. And we peeked at the implementation of arrays, not because we'd ever want to code our own array implementation and address calculation and all that, but because if you understand how these structures are built, it really helps you know about and remember their assumptions, their limitations, and their performance. This is all part of becoming what I'm calling an informed consumer of data structures. That's what you want to be when you come out of this class, an informed consumer of data structures. You know what they mean, and you know which one to use. And this is a good place to start. Using the right data structure makes your project very much easier, can make it very much easier. Choosing the wrong data structure can make your project very difficult to code, and that both choices can have big performance implications. So it's important to know that stuff. Here's a cool link, by the way, that will help with some of the big O stuff. If you want to know the big O values for certain common operations like sorting, this has got a really nice, a good table and a really nice chart that shows you how bad something like order n squared really is in terms of performance relative even to order n. That's all I've got for now. Thanks a lot, folks.